Hello, class. Welcome to week 9, where we will be talking about the inferences on the population mean. Now, I do want to be clear that this week's lecture does have very limited new material. Really, just two concepts are going to be new. This was done on purpose. I would like you to use the extra time this week to go over your midterm exam when you get it back and make sure you learn from your mistakes and figure out anything that you may have been confused on. So the objectives for this class lecture is going to be reviewing how to do the hypothesis test and confidence interval for mu when sigma, that is the population standard deviation, is known. And then we will also examine the case for both hypothesis test and confidence interval when sigma is unknown. Next week, we'll be doing confidence intervals and hypothesis test for population proportions, variance, and then we will take a look at some of the assumptions necessary for these tests. So just getting started, I will try to go through this first part rather quickly because it is a review. So let's recall the steps for hypothesis testing. So step 1, we state the hypothesis, acceptable alpha level, and check our model and any necessary assumptions. 2, we calculate our test statistic. Step 3, we define the rejection region and make a statistical decision, that is to reject or fail to reject our null hypothesis. And then step 4, we will state our conclusion in the context of the problem. So reviewing our hypothesis test for one population mean, first we want to know if there is sufficient evidence to conclude that the population mean is either less than, greater than, or different than some specified value. Those terms, less than, greater than, or different, to help us outline whether we are performing a left-tailed test, right-tailed test, or a two-tailed test. And for us, our evidence is based on our sample size, sample mean, and either the population standard deviation sigma or the sample standard deviation S. The first part of this lecture focuses on when we have sigma. The second concept we will examine in this lecture is when we have our sample standard deviation. So going through the steps, for our step 1, our stating of the hypothesis, there are 3 options for hypothesis. Our null hypothesis is always going to state that mu equals mu naught, but what can alter is our alternative hypothesis based on the scenario we're given. Recall, it'll either be a two-tailed, right-tailed, or a left-tailed test. Also, we need to specify our model and check our assumptions in step 1. Since we do know the population standard deviation, and we are working with the knowledge of having a mean, the population mean, and the population standard deviation, we can compare this to the normal distribution. And so we will be using our understanding of sampling distributions of the mean, and we also need to assume that we have a random sample. Step 2, we calculate our test statistic. When we have the population standard deviation, our test statistic is z equal to the sample mean minus our hypothesized value divided by sigma divided by the square root of n. Step 3, we define our rejection region and make our statistical decision. Now, we can define our rejection region using our critical value, and the rules are as follows. If our alternative hypothesis is mu less than mu naught, then we will reject our null hypothesis if z is less than negative z alpha. If mu is not equal to mu naught, then we will reject the null hypothesis if the absolute value of z is greater than z alpha over 2. And if mu is greater than mu naught, then we reject the null hypothesis if z is greater than z alpha. If this is not the case, then we will fail to reject the null hypothesis. Remember, we never accept the null hypothesis. We can, of course, use the p-value method as an alternative. If mu is less than mu naught, then our p-value is the probability of z less than our test statistic. If mu is not equal to mu naught, then our p-value is 2 times the probability of z being greater than our absolute value of our test statistic. And if mu is greater than mu naught, then the p-value is the probability of z being greater than our test statistic. And since we are using our z table, we would then have to use the complement rule. So if we are using the p-value method, remember if our p-value is less than or equal to alpha, we reject our null hypothesis. If it is not that case, then we fail to reject the null hypothesis. And either way, we will have to make our way to step 4 to state our conclusion. If we have a null hypothesis that is rejected, then our conclusion will be at the alpha level of significance, we do have sufficient evidence to say that whatever our alternative hypothesis is true. And then if our null hypothesis is not rejected, then we say at the alpha level of significance, we do not have sufficient evidence to say that our alternative hypothesis is true. And again, that underlined part should be filled in with the appropriate problem context. I've said this before, I'll say it again, you must include context when you're making conclusions and interpretations. If you don't provide context, then I generally take that to mean you don't truly understand what you're doing or understand the concept. So let's do one quick example with this. Lasers can provide highly accurate measurements of small movements. To determine the accuracy of such a laser, it is used to take 100 measurements of a known quantity. The sample mean error was 25 μm with a population standard deviation of 60 μm. If the laser is properly calibrated, the average should be 0. Do you believe that the laser is properly calibrated? And we'd like to use alpha at the 0.05 level. So to begin, we need to start off by recording what any information we have so I don't have to flip back and forth. So we have a sample size of 100, a sample mean of 25 μm, a population variance of 60 μm, and we know that our hypothesized value should be 0, and that we are given that our alpha level is 0.05. So first we can begin with our step 1, which is stating our null and all alternative hypothesis. So we have that mu is equal to 0 to the alternative of mu not being equal to 0. We assume in this case that all assumptions have been met. Now we can begin step 2 by calculating our test statistic. So this will be 25 minus 0 divided by 60, which is divided by the square root of 100. If we type this into our calculators, we will get 4.1667. And for us, if we decide to go with the rejection region method, then we will reject our null hypothesis if the absolute value of z is greater than z alpha over 2. And since it's a two-sided test, alpha is 0.05, we know that means our z alpha over 2 is 1.96. And so we can see that 4.1667 is clearly greater than 1.96, so therefore we can easily reject our null hypothesis. We do have the option of doing the p-value method. I will do that in this example, just as a nice review. So for us, that we may recall that our p-value, since it is a two-sided test, will be 2 times the probability of z being greater than the absolute value of our test statistic. which in this case is probability of Z being greater than 4.1667. And this is a pretty large value if we think about it using our 68, 95, 99.7 rule. So I'm going to keep these notifications. I do want to pull up our Z table. And so we have to find the probability of Z being greater than 4.1, we'll say 7 if we round it. And we can notice that this does go off our Z table. And what we do in that case is we don't know what it is exactly, but we can make an estimate. So going off the chart, we have 3.49 has the probability of, or should I say Z being less than or equal to 3.49 has a probability of being 0.9998. Using our complement rule, that means it is at 0.0002. So what this tells us is that the probability of this event occurring is going to be very small. And so in general, we would say that this means that this is the p-value is going to be somewhere less than 0.001. We also could have said less than 0.002, but either way, it is significantly smaller, and we can clearly reject our null hypothesis. So this brings us to our last step, which is to state our conclusion. So we can say at the 5% significance level, there is sufficient evidence to infer that the mean error is not 0 mu m, and the laser is not properly calibrated. Now, even looking at our results, this should have actually been a pretty logical conclusion given that we had a sample mean of 25 mu m, and the goal was to be at 0 mu m, and our standard deviation was 60. So that gave us a pretty good indication that we had some problems. But now we have it proven to be true. And that is something very important in statistics. Sometimes the answers can be obvious, but isn't sufficient to say, yeah, I looked at the mean and it was way off. We do actually have to prove it statistically because we are statisticians and scientists. And so looking at something isn't sufficient. We have to prove it. Okay, so that brings us to the end of that part of our review. Now taking a look at the second part of our review, which is to review confidence intervals for mu when sigma is known. So if we recall, if our sample mean is the mean of a random sample of size n from a population with variance sigma squared, a 100 times 1 minus alpha % confidence interval for mu is given by the following formula of our sample mean plus or minus z alpha over 2 multiplied by sigma divided by the square root n. So a quick example for this. Oven thermostats were tested by setting them to 350 degrees Fahrenheit and measuring the actual temperature of the oven. In a sample of 67 thermostats, the average temperature was 348.2 degrees Fahrenheit, and the true standard deviation was 5.1 degrees Fahrenheit. Find a 90% confidence interval for the mean oven temperature. So as always, I like to write out all the information I have so I don't have to flip back and forth with the problem. So we were given a sample size of 67, a sample mean of 348.2 degrees Fahrenheit, and a true standard deviation of 5.1 degrees Fahrenheit. And we were asked to calculate a 90% confidence level. So setting this problem up, this would be 3.84.2 plus or minus our confidence interval, which we can take a moment to look up, multiplied by 5.1 divided by the square root of our sample size, which is 67. So taking the moment to look up our confidence level, because I didn't do that in the previous problem. Yes, I want to keep my ink notifications. And so what we're going to do, we want the 90% confidence level, which implies that we are going to be having an alpha level of 0.05. And we need to cut that in half, so that would be 0.05. And there's two ways we can find this value, recognizing that we would be looking for the alpha level of 0.05, knowing that it would give us a z-value that's negative, and we can then just drop the negative to get our confidence level, or we can do 1 minus alpha, which would be 0.95. I prefer to just find 0.05 directly and then drop the negative sign, but that's my own personal preference. So if getting as close as we can, we have our critical value as close as we can get is between 0.0505 and 0.0495. So this would be 1.6, and halfway between 0.04 and 0.05 would be 4.5. So this would give us a confidence level of 1.645. Again, if we wanted to do it the opposite way, we wanted to get as close as 0.95 as possible. And that would be right here. We have 0.9495 and 0.9505. And once again, this would just give us 1.6 and exactly halfway between 0.04 and 0.05. Either way you prefer to do that, that is perfectly fine. We all have our preferences. But regardless, we should come to the correct conclusion that our critical value is 1.645. And again, in general, when we're calculating a critical value with this, unless it's easily exactly halfway between, we generally select the confidence level that is closest. So now we can use our skills of basic mathematics to plug into our calculators and get our confidence interval. And so this would become 347. Oops, I made a typo, didn't I? And just scratched off. So this should be 348.2. Sorry about that. And so then our confidence level should be 347.175 to 349.225. And then we can make our proper interpretation that would say at 90% confidence, the true average temperature of an oven set to 350 degrees Fahrenheit is between 347.175 degrees Fahrenheit and 349.225 degrees Fahrenheit. And if you think about this logically, we do know that this confidence interval shows equivalence to the two-sided hypothesis test at alpha equals 10%, or 0.10. So we actually could infer by this confidence interval that the oven is actually not reaching the stated temperature because our confidence interval doesn't include the stated temperature of 350 degrees Fahrenheit. Something to be aware of in the case that it ever comes up. All right, so continuing on with this example, how many thermostats must be sampled so that the average oven temperature is within 0.8 degrees Fahrenheit? So we know that our margin of error is equal to our confidence level multiplied by our variance, or excuse me, standard deviation divided by the square root of n. So plugging in what we know, this would be 0.8 equals our confidence level from before of 1.645. We would assume it stayed the same unless stated otherwise. Our variance was given to be 5.1, and now we just need to solve for n. So rearranging this equation, we could find that n equals 5.1 divided by 0.8 divided by 1.645, all of this squared. This isn't exactly the formula I gave you in the previous lecture. It is equivalent if you rearrange the fractions. I prefer solving it this way just because if I was actually solving for n, the first thing I would do was divide 1.645 on each side and then divide that quantity by 5.1 and then square it. But you will still get the same answer, which in this case would be n equal to 109.975, or in other words, we would need to sample 110 ovens. So very good. This brings us to the end of our review. If you skipped through, then here's the time to start playing the video because the new material has begun. And I do want to remind you that this process that we did for hypothesis testing and confidence interval for mu when our sigma is known will be followed through all the other hypothesis test and confidence interval procedures that we look at. That four-step process stays the same. Really, the only differences that we see are in the null hypothesis. Our parameters might be different. If we're working with the population proportion, then it's a p. If it's standard deviation or sigma or variance, then it is sigma or sigma squared. And then we might be comparing to different distributions, as we'll see in the next section. We don't always use the z distribution. Sometimes we use the t distribution or chi-square distributions. So this brings us to our third objective, which is the hypothesis test for mu when sigma is unknown. So beginning with step 1, this first step is exactly the same as in our review, which is why I spent so much time on the review. So our hypothesis still has those three options where the null hypothesis is going to always stay that mu equals mu naught, but the alternative changes depending on whether we are doing a one-tailed, two-tailed test. So as far as checking our model assumptions, since we do not know our population standard deviation, that means we can't use the normal distribution. And so we have to use what's kind of the next or closest thing, and that is to use the t distribution with n-1 degrees of freedom. And we also have to assume that we do have a random sample that comes from a normal population. Our test statistic, you'll see, is very similar for our hypothesis test when mu is known and sigma is unknown, and that is our test statistic is t equals our sample mean minus our hypothesized value divided by our sample standard deviation divided by the square root of n. So really the only two things that are different is that we are comparing this to a t distribution instead of the normal distribution, and instead of using sigma, we use s. Step 3, we define our rejection region and make a statistical decision. As we are using the t-distribution to compare, not the normal distribution, we'll need to use the t-table. To find the critical value, we need to know the alpha level and our degrees of freedom. In this case, again, our degrees of freedom are n minus 1. And our rules for making our statistical decision are almost identical to that with the normal distribution, only instead of z's, we have t's. So if mu is less than mu naught, then we will reject our null hypothesis if t is less than negative t alpha. If mu is not equal to mu naught, then we will reject our null hypothesis if the absolute value of t is greater than t alpha over 2. And if mu is greater than mu naught, then we will reject the null hypothesis if t is greater than t alpha. Otherwise, we fail to reject the null hypothesis. If we want to calculate the p-value and make our decision that way, it is a bit more difficult. When you were using the z-table, you were able to pretty much get the p-value exactly. In this case, the best we can really get is an approximation. And how we do that is we take our test statistic and we find the range of values that it would have lied between. So hypothetically speaking, say that we had a sample of 5, which would imply our degrees of freedom is equal to 4, and we were given an alpha level of 0.05, and we'll assume this is a one-sided test. And so we then, hypothetically, we got our test statistic, and we know that our test statistic, we'll say, is 3.21. So what we need to do using our degrees of freedom of 4, we examine this whole row and try to find where that 3.21 would lie between. And so taking a look, we would see that 3.21 would be between 2.7764 and 3.7469. So going up, that tells us that our p-value would be between 0.025 and 0.01. So again, it doesn't give it to us exactly, but it does give us a range. And so you may be asking what happens at the end. So if we had a test statistic that was greater than 8.6103, then that means our p-value would be less than 0.0005. And if our test statistic was less than 0.7407, then we would assume that the p-value is greater than 0.25. This isn't ideal because we can't get it exact, but we can make the range, and usually from the range we can make a clear decision. So in general, I would prefer you to use the rejection region method because it is more exact, but I will expect you to know both methods. And as far as making your decision from your p-value, it is the exact same as when sigma was known. If our p-value is less than or equal to alpha, we reject the null hypothesis. If p is greater than alpha, we fail to reject the null hypothesis. And as far as our fourth step, where we state our conclusion, it is the exact same as the case when sigma was known. If we reject the null hypothesis, then we say at the alpha level of significance, we do not have sufficient evidence to say that the alternative hypothesis is true. And then if we do not reject the null hypothesis, we state that at the alpha level of significance, we do not have sufficient evidence to say our alternative hypothesis is true. And as always, that alternative hypothesis is true statement should be in the context of the problem. Okay, so this brings us to the part where we can actually do a few examples. I do have about 3 examples I want to go through, and each of the cases will be a different scenario of the 3 different options for the alternative hypothesis. And so let's get started. So a rental car fleet owner suspects the mean annual mileage of his cars is greater than the national average of 12,000 miles. He selects a random sample of 25 cars and calculates the sample mean to be 12,375 miles and the sample standard deviation to be 2,415 miles. And we'll let our significance level be alpha equals 0.05. So going on to our next slide, same as always, let's write out what we know. So we have a sample size of 225. Nope, I apologize. That was a typo on my part, not 225, 25. A sample mean of 12,375, a hypothesized value of 12,000, and a sample standard deviation of 2,415, and we were also given that our alpha is 0.05. So setting it up, we were asked to find if the gas mileage was greater than. So our null hypothesis would be mu equals 12,000, and then our alternative would be mu is greater than 12,000, because we want to see if the gas mileage is greater than the stated average of the 12,000 miles. Step 2, then, we can state our test statistic and calculate it. So remember, it will be t minus our sample mean of 12,375 minus our hypothesized value, 12,000, divided by our sample standard deviation of 2,415, divided by our sample size of 25. Putting this into our calculators, we would get a test statistic of 0.7764. And remember, anytime you're calculating something, it is safe to round it to the 4 decimals. This now brings us to our third step, which is where we can define our critical region and make a decision. So for us, we can say that we will reject the null hypothesis if t is greater than t alpha. We know that t is 0.7764. At this point, let's close out of here and take a look at our t-table. Okay, so we were told that our alpha was the 0.05, and we get to use that because it is not a two-sided test. So using our information of our alpha being 0.05 and the degrees of freedom, we were told that our sample size was 25, so we need to do 1 minus, which would be 24. So looking under the 0.05 heading, we need to find degrees of freedom equal to 24. And there we have it. Our critical value is going to be, in this case, 1.7109. Going back to our slides, so we now know that T alpha is 1.7109, which we can see is not greater than, or rather, sorry, our 0.7764 is not greater than 1.7109. So therefore, we can safely fail to reject our null hypothesis. This brings us to the part where we can state our conclusion and say that at 5% significance level, there is insufficient evidence to infer that the rental car fleet has greater gas mileage than the average of 12,000 miles. Very good. So that brings us to the end example 1, except for I would like to go ahead and take a look at the p-value method just so we can have some practice with it. So with the p-value method, we need to know what is our degrees of freedom and our test statistic. So our test statistic is 0.7764, and we have degrees of freedom of 24. So we may recall that we would reject our null hypothesis if p is greater than alpha, which is 0.05. To find our p-value, it is the probability of t being greater than 0.7764. And as we know, we should expect to find a range. And if we do it correctly, we should also conclude to fail to reject our null hypothesis. Let's take a look. So what we can do is we take a look at our row that has our degrees of freedom of 24, and we need to find where our values would lie between, which we can see that 0.7764 would in fact lie between 0.6848 and 1.3178. So if we scroll up, that tells us that our p-value is going to be between 0.25 and 0.10. And both of these values, even if the p-value was 0.10, either way we would conclude that that p-value is definitely greater than alpha, so we should, oops, sorry, typo, we will reject if our p-value is less than or equal to alpha. I'm sure you guys caught that one before I did. But in this case, so we would fail to reject our null hypothesis. So sorry about that. Remember, we reject our null hypothesis if p is less than alpha. Sorry about that, and we can clearly see that our p-value is not less than alpha, so we must fail to reject our null hypothesis. And our conclusion would be the same regardless of the method we use. Okay, so at this point, let's take a look at another example. Okay, so a drug company is concerned that its 500 milligram aspirin tablets may contain too much or too little aspirin. Suppose the company selects a random sample of 100 tablets and finds that they have a mean weight of 501.5 milligrams and a standard deviation of 7 milligrams. Let's have alpha be 0.01, which makes sense because generally when we are concerned about things that have to do with the medical profession, we'd rather be more certain than not. So let us begin by recording everything that we know already. So we have a sample size of 100, a sample mean of 501.5, a sample standard deviation of 7, an alpha level of 0.01, and a hypothesized value, or that stated value, of 500. Now, because this is a two-sided test, because we were asked to find too little or too much, we can state that our null hypothesis will be mu equal to 500, and our alternative hypothesis will be mu not equal to 500. This brings us to our second step, which is to calculate our test statistic. We will do our sample mean minus our hypothesized value, all divided by our sample standard deviation divided by the square root of our sample size. If we plug this into our calculator, we will get 2.1429. This now brings us to the step where we can make our decision. For us, we can then say that we will reject our null hypothesis if the absolute value of t is greater than t alpha over 2. We were given that alpha is 0.01, so that means alpha over 2 would be 0.005. We also need to know our degrees of freedom, which is n minus 1, so this would imply that our degrees of freedom is 99. So at this point, I'm going to exit out of here and pull up our t-table. So our t-table, we will be looking for the joint of our alpha over 2, which is that 0.005, and our degrees of freedom of 99. So we can see that this table doesn't exactly give us 99, but it gives us 90 and 105. When we are in the case where we don't have it exactly, it is acceptable to go to the nearest critical value. So in this case, 105 is closer than 90, so we'll use the critical value for 105. And so this would give us a critical value of 2.6235. Double checking I'm in the right column. Yep. So very good. This means we can go back to our previous slide. But before we do that, I do want to draw your attention because I know it can be a little off-putting to not have it exact. So if you notice that the critical value, if we had used the 90, would have been 2.3685, and we used 2.3624. So the difference between these two critical values is less than 100th. And so basically, either one you use, you'd probably still get the same conclusion. But just to be aware that when it gets up to the higher levels of a sample size, we don't see a huge difference in our critical values, which is why they start skipping values on the chart. Save space. All right, so again, our critical value is approximately 2.6235. And we can see that although close, our test statistic is not greater than our critical value. So once again, we will need to conclude that we should fail to reject our null hypothesis. And so what we can say for our conclusion, at the 1% significance level, there is insufficient evidence that the mean aspirin amount differs from the stated amount. All right, very good. Let's move on. Example 3. A random sample of 50 homes sold in Denver in 2010 had a mean price of $221,000 and a standard deviation of 50,000. Can we conclude that the population mean price in 2010 is less than 235,300? We'll use alpha at the 10% level for this one. Okay, so as always, let's start with what we know. We have a sample size of 50, a sample mean of 221,000, a sample standard deviation of 50,000, a hypothesized value that we're comparing to of 235,300. We were told that our alpha was at 10%. The problem implied that this was a one-sided test, so we won't need that alpha over 2, but we will need to know that our degrees of freedom would be 49. This brings us to our step 1, which is to write out our hypothesis test. Our null hypothesis, as always, will be 235,300. Remember, always equal when we are doing our null hypothesis, because we assume that the null hypothesis is where things stayed the same. Now, we were asked in the problem, can we conclude that the population mean price in 2010 is less than? So that's going to imply that our alternative hypothesis should be less than our 235,300. This brings us to our second step, our test statistic. T will be 221,000 minus 235,300 all over 50,000 divided by the square root of 50. If we plug this into our calculators, we should get a test statistic of negative 2.022. So we can now go to our third step where we reject our null hypothesis if t is less than negative t alpha. So exiting out of here for the moment, we can take a look at our t-table. Again, we are going to be looking where we have alpha at 0.10 and degrees of freedom of 49. So we can see that at the 10% level, following down that column, we do not have a case where the degrees of freedom is 49, but we do have 50, and so we will say that's close enough. And so our critical value in this case will be 1.2987. Again, we need to make that negative. So our critical value is negative 1.2987, which if we compare it to negative 2.022, we can see that yes, our test statistic is less than our critical value. So therefore, we may conclude that we must reject our null hypothesis. And so we will say at the 10% significance level, there is sufficient evidence to infer that the population mean price of a home sold in 2010 in Denver was less than $235,300. Very good. And in case you were curious, I will leave you to check it on your own. But if you use the table to find the p-value, your p-value would be equal to the probability of z being less than 2.022. And so if you use the table with the degrees of freedom at 50 and following along that row, you would see that your p-value would be between 0.05 and 0.02. Nope, I'm sorry, that's off. I was looking at the problem we just did. Our p-value would be between 0.025 and 0.01. And so you would still conclude that you should reject the null hypothesis. All right, so this brings us to the end of talking about the hypothesis test for mu when sigma is unknown. And so this brings us to the last part of this lecture, which is to talk about confidence intervals. So confidence intervals for mu when sigma is unknown. We will use our sample standard deviation S instead of our population standard deviation sigma. We can recall that our test statistic is equal to our sample mean minus mu over the sample standard deviation divided by the square root of n, and it follows the t-distribution with n minus 1 degrees of freedom. So if we are using the t-distribution, we can see that the probability of negative t alpha over 2 less than t alpha over 2 would be equal to 1 minus alpha, which we then could use to derive to find that our 100 times 1 minus alpha percent confidence interval for mu when sigma is unknown is the sample mean plus or minus t alpha over 2 multiplied by our sample standard deviation divided by the square root of n. And just for fun, we can take a few minutes to quickly prove that. So we were given, and we know that the probability of negative t alpha over 2 less than t alpha over 2 is equal to 1 minus alpha. If we substitute for our value of t, we have that the probability of negative t alpha over 2 is less than our sample mean minus mu over the sample standard deviation divided by the square root of n, which is less than t alpha over 2, which equals 1 minus alpha. At this point, we're going to solve that middle equation for mu, because we were trying to calculate a confidence interval for mu, so we want that mu to be in the center. So we'd start off by multiplying both sides of our equation by our sample standard deviation divided by the square root of n. So this would be negative t alpha over 2 multiplied by s divided by the square root of n, which is less than our sample mean minus mu, which is less than t alpha over 2 multiplied by s divided by the square root of n, which is still equal to 1 minus alpha. And then isolating our mu, this would give us a probability of our sample mean minus t alpha over 2 multiplied by s divided by the square root of n is less than mu, which is less than our sample mean plus t alpha over 2 multiplied by the s divided by the square root of n, which equals our area of 1 minus alpha. And so therefore, we can see that our confidence interval for mu would be our sample mean plus or minus t alpha over 2 multiplied by our sample standard deviation divided by the square root of n. So let's do a couple quick examples. So first, we have a random sample of size 30 babies from our 1998 birth data. The sample mean birth weight is 3,498.7 grams, and the sample standard deviation is 434.2 grams. We'd like to create a 90% confidence interval for the population mean birth weight mu. So we're given that our sample size is 30, our sample mean is 3,498.7, our sample standard deviation is 434.2. We were asked to construct a 90% confidence level, so that would imply that our alpha is 0.10. And since this is a confidence interval, that means we are really needing alpha over 2, which would be 0.05. Now we can use the t-distribution table to get our critical value. To do that, we need to know our alpha over 2, which is 0.05, and our degrees of freedom, which is n minus 1. So our degrees of freedom would be 29. So if we look in our table, we'll get a critical value of 1.699, but let's check it out to be sure. So pulling up our t-table, again, our critical value would be 0.05 and degrees of freedom of 29. And so there we have it right here, 1.6991. I see I dropped the 1, but that's all right. Not a big deal. So therefore, we can now just plug into our equation. Our sample mean would be 3,498.7 plus or minus 1.699 multiplied by 434.2 divided by the square root of 30. So our confidence interval would go from 3,364.0 to 3,633.4. So to state it properly, we are 90% confident that the interval from 3,364 to 3,633.4 grams contains the true population mean birth weight of U.S. babies born in 1998. Excellent. Not bad, I hope. Let's take a look at a second example. This one I'll work out a little slower. So the concentration of carbon monoxide, CO, in a gas sample of size 27 is measured by a spectrophotometer and found the sample average to be 85 ppm with an uncertainty of 64 ppm. Find and interpret a 95% confidence interval. So to begin, as always, I like to state everything that we have. We have a sample mean of 85, a uncertainty level, which would be the sample variance of 64, which we could go ahead and take the square root. That would give us a standard deviation of 8. We were given that the sample size is 27. We were asked to calculate a 95% confidence level. This implies that our alpha is going to be 0.025, or excuse me, our alpha level is 0.05, which implies that our alpha over 2 is 0.025. Jumped the gun a little. And since we have a sample size of 27, this implies that our degrees of freedom would be 26. Now at this point, we have pretty much everything we need except for that critical value to solve our problem. Well, we can set everything up just in case. Well, not just in case, but we can set it up minus the critical value. So it would be 85 plus or minus, leaving space for our critical value, the square root of 64 over 27. Now we can go ahead and get our critical value. Remember, we'll need two pieces of information, our alpha over 2 and our degrees of freedom. So this would be 0.025 and 26. So looking at our t-table, 0.025 and 26 would give us a critical value of 2.0555. Excellent. Let's go back, plugging in 2.0555. Now we can just plug and chug. So this would give us a confidence interval of 81.8354 to 88.1646. Now to give us a proper interpretation, we can say with 95% confidence, the true mean concentration of carbon monoxide is between 81.8354 ppm and 88.1646 ppm. I know sometimes it is tempted to be lazy to write, from the above confidence interval instead of writing out the numbers. That is not acceptable. You do need to write the whole thing out. Be detailed, please. Okay, so let's move on. Take a look at another example. And this question is going to be in two parts, just as a heads up. So we're told that 5 students are visiting the Student Health Center for a free dental examination during National Dental Hygiene Month. And they were asked how many months that had passed since their last visit to the dentist. Their responses were as follows: 6 months, 17 months, 11 months, 22 months, and 29 months. Assuming that these 5 students can be considered a random sample of all students participating in the free checkup program, let's go ahead and construct a 95% confidence interval for the mean number of months that lapsed since their last visit to the dentist. Okay, so the first thing that we were given was our sample, which was 6, 17, 11, 22, and 29. We can see that this sample has 5 individuals, which would mean that our degrees of freedom is going to be 4. And we were asked to construct a 95% confidence interval, which means we're going to need an alpha over 2 value of 0.025. We were not given our sample mean and sample standard deviation or sample variance, so we are going to need to calculate that. So we can recall that our sample mean is the summation of our xi over n. So this would be 6 plus 17 plus 11 plus 22 plus 29. That is equal to 85 divided by our sample size of 5. So this will give us a sample mean of 17. We can then calculate our sample variance, which is that summation of x equals 1 to 5 of xi minus our sample mean squared, all divided by n minus 1. And I will tell you that that summation of x equals 1 to 5 is equal to 326. I'll leave you to calculate it by hand on your own. Divided by 4, 5 minus 1 is 4, and this gives us a sample variance of 81.5, or a sample standard deviation of 9.027735. So at this point, we have pretty much everything we need to set up our confidence interval. It will be 17 plus or minus our critical value, which we'll find in a minute, multiplied by the square root of 81.5 divided by 5. Let's take a moment and find our critical value. So we have that our degrees of freedom is equal to 4, and then our alpha over 2 is 0.025. Okay, so 0.025, degrees of freedom 4, so this would mean our confidence level or critical value is 2.7764. We can now go back to our slide, plugging in 2.7764. Now using our calculators, we can plug and chug. And so this would be 5.7908 to 28.2092. And again, if I don't know, I always round to 4 decimal places. It's a good rule of thumb. And so we can now make a proper interpretation and state that we are 95% confident that the true average lapse time in months is between 5.7908 and 28.2092 months. So in this case, I included the fractions of the months. And we can always make a statement like, if we round to the nearest month, because logically, if people are recording like, oh, how long has it been since you were at the dentist, they're not going to be like, oh, it's been 5.7 months. No, they're going to say that it's been between 6 to 28 months, which is honestly a more logical interpretation. So if this had been me writing this out as like a problem, I would have written 6 to 28 months, because that would have been the logical units. If somebody was recorded and asked when was the last time you went to the dentist, they would have said 6 months, not 5.78. But since we did calculate it out exactly, I did also want to include it in this interpretation. And in case you were wondering, 28 months, that's a little, oh, it's 2 1/3 a year. All right, so this brings us to the last part of this lecture. I think there's 2 slides left. And this final example is an extension of the example we just looked at. So using the scenario described in example 3, what would the sample size need to be if we wish to be 99% confident and within 0.05? Now, already looking at that within 0.05, that is going to be kind of a tough sell. If we looked at our previous confidence level, it was 5.7 to 28.2, with our sample mean being the center of 17. So we should expect that this confidence, or rather the sample size, is going to need to be pretty large, also because we're using a 99% confidence limit. So let's see, but we've never really done a sample size that ended up being super large, so I'm expecting this one to be. All right, so from our previous, we know our sample variance is 81.5. We want to be 99% confidence, so that implies that our test statistic, our alpha value will be 0.01, which we'll need to cut in half. So our value of interest for our significance level, that alpha over 2, is going to be 0.005. So we can go ahead, calculate that critical value, because once again, we still know that we don't know our degrees of freedom, but we can use the previous one in this case to get a confidence level. Or at least we will. So 0.005, so we're going to let our confidence level be the 4.6041. Again, we're going to use that sample we had previously, which may not be fully logical. And so we probably, in that case, would have assumed, logically, if we were doing this, we might have needed to use a sample size that was larger, but I'm saying in this case, let's go ahead and use, since we're using the sample variance that we calculated in the previous slide, let's go ahead and use that same degrees of freedom level for our critical value. So that 4.6041 will let be our confidence level. And now we'll set up our problem to solve for n. So this will be 0.05 equal to 4.6041 multiplied by the square root of 81.5 over the square root of n. So our n would be equal to 81.5 all divided by 0.05 divided by 4.6041 and quantity squared. And if we type this into the calculator, we will have our sample size, our necessarily sample size would be 691,046. So, kind of interesting, but nice to think about that that is a very large sample size we would need to take in order to be that accurate. Probably not going to happen. We'd have to make exceptions to that. All right, so to end this lecture, just wanted to talk about some assumptions we need when we're constructing a confidence interval for mu. One, we have to have a simple random sample from the population. And at the minimum, we do need to be sure that our data values are independent. And two, our sample comes from a population of values that does follow the normal distribution or is at least nearly normal, or we need to have a sample size large enough that the condition can be relaxed due to the central limit theorem. All right, so that brings us to the end of this week's lecture. Let me remind you, when your midterm exam grades are posted, please review the exam, see what you missed, learn from your mistakes now so you don't have to do it at the end of the semester right before the final. All right, have a good week, and I will, well, not see you, but hopefully hear from you soon. Have a good night.